Okay, now let's have a look at these ones. Once we have the value for the area, I find using a pressure law. Pressure equals to force over area. Now I rearrange that one for the force. Force at B is equal to area at B multiplied by pressure at B. But here I put the pressure at A. The reason is because the pressure at A is same as pressure at B. And we already find out the pressure at A, which is here. I'm not going to use 0.64 megapascal. I am going to use Newton over millimeter square. The reason is because here the area, which is here, I got pi r square. I have that value in millimeter square, so they will cancel out. So I got 0.6366 Newton meter square and the area value from here. And I got an answer around 1800 Newton. Now there is an easier way of doing that one, much quicker way of doing that one. Now I'm just going to show you how we can do much quicker way and easier way. If we have a look here, what was the force here? Force was 200, and according to our calculations, the force here is around, let's call it 1800. Yeah, 1800 Newton. Yep. So how much force is around 900? Is it 9 times more, isn't it? Yeah, 9 times more. Okay. Now if I go to next page, and if I clear the screen, so the force uh, at A and the area, area diameter at A. Yeah, so force at A is 200, yeah, Newton, and diameter was 20 millimeter. Yeah, and at the B, force at if I change the color to that one, force at B we didn't know, but well, we know it's 1800 Newton, and the diameter is 60 millimeter. Or not diameter, not square. Now the easier way of doing that one is what you did with this bit. What's the ratio between that and that? The ratio between that one is 1:3. So you increase the dia 3 times. Now area is actually square. There is a square in the area. So what you need to do is then you square that thing. So 3 square, which is the schematic, like online thing, so I accidentally found it, but yeah, it paused, so this is good. Yeah, it's saved. um, when we look at this diameter, this is 20 and the diameter on the other side is 60. So diameter on this side, first we find out the ratio between the diameter. I have to multiply this diameter. Doesn't matter if you convert into radius, that will be 10 and that will be 30, so the ratio remains the same. So I have to multiply this dia by 3 times to convert into the dia on the other side. So I've increased the diameter by 3 times. When I increase the diameter by 3 times, what actually happened is, actually I need to square it. So when I square that one, that's 9, and this is what you need to multiply that with. 200 times 9 will give you an answer of 1800. Now, there are few laws we need to follow. One of the thing about Pascal triangle is that Pascal triangle is independent of the shape. Now, does not matter whatever the shape of the container is, it will obey the Pascal's law. We need to understand one other thing. This is our assumption we make, that the fluid is incompressible, that you cannot compress the fluid. If we are applying the Pascal law somewhere where the fluid is compressible, some power is transmitted uh, during the compressibility. Now, pressure we represent with P. Units of pressure we go as a Pascal, we write as a Pascal, as a PA, Pascal. Um, because the pressure we see in the hydraulic is quite large, so usually we go either megapascal. Now, megapascal is 10 to the 6 Pascal, so million Pascal, or we go gigapascal. Gigapascal is 10 to the 9 Pascal. And same as force, kilopascal is 10 to the 3. If that's a kilopascal, we use a lowercase k. That is 10 to the 3 Pascal. So it goes up in 3. Same as force. Force we can have either in kilonewton, meganewton, or giganewton. That's the equation. If you want to find out the force, we rearrange that one. If let me do that one. We get the pressure equals force over area. This is if you want to find out the pressure. If you want to find out the area is force over pressure. If we want to find out the force, we can rearrange the formula as pressure times area. Yeah, so it's like a triangle thing. Yes, perfect. Now the next thing is expansion of a liquid and incompressibility. For the purpose of pneumatic and hydraulic, let's consider the hydraulic. We assume the fluids are not compressible. Under extremely high pressure, the volume of the fluid can decrease. But this decrease is negligible. We can ignore that decrease. Usually, this decrease is, imagine if we have a system which doesn't leak at all, and when we compress that thing, it might be because there are some air bubbles present in there which are you compressing. It might be there are some cracks that might develop into the system and fluid is actually going into that crack or that system. Now, all the liquids, they expand and they contract because of the temporal change, temperature change. It might be when you are actually compressing the fluid, there is a change in temperature from one on the other side, so the fluid has compressed. But usually when you compress something, it gets hot, so it should actually expand. So sometime this is all balanced into the system. Now, if something expands because of the temperature change, it exerts an extra pressure. So imagine the pressure you're getting was 100 megapascal, but pressure you're getting on the other side is 100.002 megapascal. So this extra pressure is because we have put, the system thinks we have put extra liquid into the system, extra fluid into the system. We haven't. The reason is because the volume of the fluid has increased, so the system thinks there is an extra fluid into the system. Now, in hydraulic gauges, hydraulic systems, all these change in the volume of the fluid with respect to the change in temperature is already calculated, and we build that a system in such a way so it compensates for that change. Now, if we have a look at this system, imagine you got a solid here and you are using a hammer and you're actually applying a force. Now all this force will be diverted is focused on in this length, yeah, this dimension. But if we got a liquid and you use a hammer, all the pressure will be distributed in all direction the pressure will be distributed. Yep. So all direction, and it's straight away the pressure is straight away felt on the other side. You can do that experiment on with a bottle. If you have an empty glass bottle, you fill it up with water, leave a little bit air on the top, and actually, if you just hit that one really hard, really quickly, so you don't let any air go, the bottom of the glass, no matter how thick it is, it's going to come off straight away. Yep. So the reason is because it cannot withstand the sudden impact force, even though it's a fluid, it's a water. It can just actually remove the bottom of the glass bottle. Okay. um Anyone got any questions so far? Yep. I'm just